Before we start the demo, I'd like to tell you some of the great features of this device. We're going to show you the MAX40007. It's a nano-powered op-amp with a wide operating range. It operates from 1.7 all the way up to 5.5 volts. What this allows you to do is it allows you to use it with 1.8 volt microcontrollers, 3.3 or 5 volt microcontrollers. So it's a very flexible solution. The second feature of this device is a 700 nanoamp quiescent current. And why is this important? The reason why is majority of the time a microcontroller is asleep. It wakes up for a short amount of time to do a reading or a function and then goes back to sleep. So having that quiescent current allows you to extend your battery life whether your product is sitting on the shelf or on your wrist. The third feature of this device that makes it an excellent device is the size itself. The package is a WLP package, which is 1.1 by 0.78 millimeters. So it's a very small package, especially for those space-constrained applications like wearables, portable medical devices, or any battery-powered device. So let's check in with Srudeep and see how he's doing. Srudeep, are you ready?
Yes.
All right, Srudeep, could you introduce yourself and your demo?
Sure, yeah. Hello there, this is Srudeep Patil, Applications Engineer in Signal Chain Products at Maxim. So today we are talking about MAX40007. Like Tom pointed out, the advantages of this nanoPower op-amp. So the main selling point of this IC is the size and the low power nature of this device. So guaranteeing the 1.7 volt supply actually provides us to enable it with the microcontroller, which uses a 1.8 volt supply. And the microcontroller might have like a 5% variation in its rail. So in that case, the microcontroller rail can go all the way to 1.7. And this IC guarantees that the op-amp works even at 1.7 volts over temperature. And one other point I would like to bring up about this IC is it has a 700 nanoamp supply current at the room temperature, but over the whole temperature range of minus 40 degrees Celsius to plus 125 degrees Celsius, it consumes under 1 microamp over the entire temperature range. So the variation is 300 nanoamps over the entire 25 to 125 degrees C, which is huge benefit for battery-powered users. And we'll walk over on the operation of the EV kit here.
Let me see if I can
So here we have a 1-inch by 1-inch board showing on the video, and you can see the tiny black dot, which is the IC. Okay, sure, yeah. So it's the IC at the center of this, and there are two jumpers on the board. There is a jumper J1 here and the jumper J2 here. So the jumper J1 is, by default, it is floating, and jumper J2, by default, it is in position 1 and 2, but today we are using it in position 2 and 3. So what this jumper J2 enables us is to use the op-amp in a split supply or the single supply mode. So today we are using it in the single supply mode. So yeah, we have it configured in position 2 and 3 here. And we have a plus 3.3 supply applied to the power supply here. We have a ground here from the power supply, and we have input positive signal applied to this test point here, and the ground return of the input here. So we can go over the operation of this device by the quick start. So we have 3.3 volts set on the input right now on the scope, as you can see here. And if you can see the schematic there, the simplified schematic is nothing but the unity gain buffer. So whatever input signal you apply on the input positive, you get the same signal on the output.
So it's just following the voltage, right?
Yeah,
right?
it's a voltage follower or a unity gain buffer, you call it. So it follows the input. So you can see the output is following the input. And we can do the same experiment with the AC signal on the input. So this part has a bandwidth of 20 kilohertz with ultra low supply current consumption. So we can have an AC signal on the input, and you can do the same get the same output from the device. So the main reason we are showing this unity gain buffer at this low power op amp is for the sensor interfacing between sensor and the ADC by itself. So what this unity gain buffer does is it isolates and it enables the high input impedance that the sensor sees, so that the ADC doesn't take the current from the sensor itself. So now that we have seen unity gain buffer operation of this device, so let's move on to the demo, which is a force sensor demo that we are doing today on this nanoPower op amp. So let me
if I could borrow the sensor while you're
yes, sure.
setting up. Okay, so while Srudeep is setting up over here, I'd like to tell you, if you could continue to connect it up. Thank you. So while Srudeep is setting up the second demo, I'm going to tell you a couple of more features about this nanoPower op amp. So it has a 300 microvolt input offset current. It operates rail to rail. It has a 20 kilohertz bandwidth, and it has a 40 picoamp input bias current. So it is a great op amp for low power applications, especially sensors. Now, as Srudeep is connecting up this system, let me tell you what he's doing. So this is a force sensor, and basically a force sensor is just a variable resistor. And so when you press on the resistor, it'll change, the force sensor, it changes the resistance. So what we're going to do is we're going to connect one end of the force sensor to VDD, and then we're going to connect the other end to the non-inverting input of the op amp. And then we're going to add a resistor to the bottom to make our resistor divider. And then what we're going to do is we're going to use a single supply mode. So we're going to connect one end of the op amp to VCC and the other to ground. And then the third step is to put it into unity gain mode, where we're going to place that jumper on pins 2 and 3. So, Srudeep, are you ready?
Yes.
If you could show the demo.
Sure. Like Tom pointed out, the force sensor is nothing but a variable resistor. So based on amount of force you apply on the sensor surface area, over here, the resistor varies. And the more the pressure, the lower the resistance it gets. So which allows more current to flow through that resistive divider there. So as you can see now, whenever I apply pressure, you can see the output of the op amp goes towards its rail. So it really depends on how much pressure I apply, and the proportional voltage will be set to the output. So the more the pressure, the more it gets, and lower the pressure, it goes down. So and this can happen at a very fast pace as well. I'm making the pressure like a dynamic AC behavior. Yes, so we have no pressure right now, no force right now, and the voltage is at low on the output.
All right, great.
And one more point I would like to tell is this op amp, like I earlier pointed out, it provides a high input impedance from the sensor which feeds into the ADC input. So this basically depends on the force that user exerts on the sensor. The ADC and the microcontroller can make a decision based on amount of force you apply. So basically this can go into a wearable, medical wearable, or a cell phone, where you exert force on the outer case of the battery, outer case of the phone by itself, and make it into a configurable action based on the force you apply on the surface area. So that's kind of a demo we outlined.